Okay. So, I wanted to finish this proof of this fact due to Lagrange that every positive integer is a sum of four squares. Um, so yesterday I had just finished this proof of that of this lemma, which is going to be a thing that makes our job here a lot easier. So let me there we go. Okay. Let me just quickly refresh. So we're trying to prove that every positive integer is a sum of four squares. The lemma that we proved yesterday is that if p is prime, then there's integers u and v such that u squared plus v squared is congruent to minus 1 mod p, or u squared plus v squared plus 1 is congruent to 0 mod p, or is divisible by p. We proved this using that slight counting argument here. But, this kind of seems like it's out of nowhere almost. So the question is, why do we need this lemma? So the idea was we wanted to prove the fact for primes and then use that somehow to say that it has to hold for composites, right, for any generic positive integer. Now we can start the proof of Lagrange's fact. I want to show this for prime. So first, we show that every prime is a sum of four squares. Okay. So let u and v be as in the lemma. So here's where our lemma that we proved yesterday shows up. So the lemma I'm referring to is this one. So say that I have a prime p, that I'm guaranteed integers u and v satisfying this congruence. So u squared plus v squared plus 1 is congruent to 0 mod p. So suppose we have those integers u and v at our disposal. Okay, so let u and v be as in that lemma. Let b be the set of points in R4 satisfying the following. U x sub 1 plus v x sub 2 plus p x sub 3 squared plus v x sub 1 minus u x sub 2 plus p x sub 4 squared plus x sub 1 squared plus x sub 2 squared is strictly less than 2p. Okay. Okay. Well, you might recall something that we talked about yesterday that brings to mind this, or a region of this very description. So yesterday I wrote out some kind of long-winded fact about determinants, which said that if you had, basically it said that if you had a region be, see if I can find it among the notes here. So if you had a region B that was defined in terms of a bunch of inequalities involving continuous functions, and you modified the arguments being plugged into those continuous functions by matrix multiplication, then the determinant of that matrix is what determined the scale factor of the volume of the region in question. So there we go, there it is. So I call this the change of variables lemma. So we had this lemma that if you have a region that is defined in terms of some list of inequalities involving functions f sub I that are all continuous functions, in terms of these bounds, where the upper bound is some on these absolute values or list of real numbers, and you have invertible matrix A, and you define a region that is the region B that's been modified by A in the following way, right? So in each slot of the function, you have the rows of B dotted with this n tuple x1 to x sub n in each slot here. So if you have region B prime that is defined in this way using the same f's now but modified or transformed by A in this way, then the absolute value of the determinant of A is what determines the scale factor between these volumes. Okay, so specifically, there was the following fact that said if I had a region that was just the standard ball of radius r centered at the origin in R4, its volume was 1/2 pi squared r to the fourth. Okay, but if I had real numbers p, u, and v and a with the following matrix, then the determinant of this matrix is p squared, which you can compute using cofactor expansion if you like. So here's my matrix A. This determinant's p squared. And so this region, which is exactly our region, right? So maybe there. So the region in question, which is the collection of points in R4 such that ux1 plus vx2 plus px3 squared plus vx1 minus ux2 plus px4 squared plus x1 squared plus x2 squared less than some r squared has volume 1/2 pi squared r to the fourth over p squared. So we're going to use this to compute the volume of this region that I just wrote out, right? So now playing the role of r squared here is 2p. So playing the role of r is square root of 2p. Okay. And so using our lemma from earlier, so this is the change of variables lemma. This is an ellipsoid with volume that is given by so the volume of this B defined thusly is 1/2 pi squared times square root of 2p to the fourth all over p squared, which is the determinant of A in that lemma. It's the determinant of the matrix in question. So simplifying all this, I get a p squared out of this, so that cancels. So this is a 2 pi squared. Okay, since I get a 4 out of this. And why do I need to compute the volume of this region B? Well, note that 2 pi squared is greater than 2 to the fourth. What's the significance of 2 to the fourth? Well, here we have a region B that is a set of some points in R4, its volume is greater than 2 to the fourth. What else is true about B? Also, note that B is centrally symmetric if you believe it's an ellipsoid. If you know what an ellipsoid looks like, then this won't take too much convincing. So it's centrally symmetric. You can also use this defining inequality to just directly show that. And convex, again, think of what an ellipsoid is shaped like. Okay. So I have a region in R4 that's centrally symmetric and convex, and its volume is greater than 2 to the fourth. Okay, so obviously I'm setting you up to use Minkowski's theorem. So by Minkowski's theorem, there exists a point x1, x2, x3, x4 in B such that it's not the origin, with integer coefficients, or coordinates, I should say. So every single one of those x sub I is an integer. Okay. Okay. Now, using the fact that those coordinates are an integer, I now want to say, okay, I have coordinates that are integers, but they satisfy this relationship, right? So what does this mean? Well, they satisfy this relationship. They're integers, and they're not all 0, right, by Minkowski's theorem. So looking at this expression, it means I have this inequality, but this has to be positive, first of all. This has to be positive because not all of these things can be 0, and just looking at this inequality, if not all of these things are 0, then this is guaranteed to be a positive quantity, right? There's squares everywhere here. Okay, so 0 is less than that inequality, which is less than 2p. Okay, so we have the following string of inequalities. But I want to look at this quantity mod p, right? But mod p, what is this quantity? So I'm not going to rewrite that right here. What is this congruent to, mod p? Well, this is congruent to, so let's see here. Mod p, these terms go away, right? And the mixed terms, so the px sub 3 and px sub 4 go away because mod p, those things are 0. So I have a square, so I have u x sub 1 plus v x sub 2 squared, v x sub 1 minus u x sub 2 squared. The mixed terms there cancel because of this minus sign. And so I can factor u and v judiciously out of what remains, and then I have this extra x sub 1 squared plus x sub 2 squared. So what do I get out of that? So after factoring, this is x sub 1 squared times u squared plus v squared plus 1 plus x sub 2 squared times u squared plus v squared plus 1 mod p. Ah, now it becomes clear why I wanted u and v satisfying this, right? So going forward, right, how would you have done this, right? If you if you didn't proceed in the way that we did, right? Which is, the efficient way, knowing how it works out. How would you have shown this? If you had the idea that Minkowski's theorem was something that you could use here, you would start out with a description of some region, maybe in coefficients here, or a description slightly more general. You would come up with a region you could actually compute the volume of to show that it satisfies this bound of Minkowski's theorem. And then when you got to this step, you would notice that you really wanted these two terms to be congruent to 0 mod p. Okay, so for us they are going to be congruent to 0 mod p because of this lemma that we have, right? And so how would you have done this if you were trying to develop this, from the ground up? So as I said, you would have started with a description of your region, try to compute the volume, make whatever assumptions you need to be able to compute the volume to say that it's definitely bigger than 2 to the 4th. And then with what's remaining, you look at this and you say, okay, so to keep going, I want this to be 0 mod p. Okay. And so for this to be 0 mod p, it's sufficient to just have a u and v from this description that make these two terms congruent to 0 mod p. But that's exactly, the existence of a u and v that do that is exactly what the lemma concerns, right? So this is what I need. Okay. And so then you would try to prove that lemma, right? And if you're successful, then you're basically going to be done. All right, and so by the lemma, this is congruent to 0, or I should say by construction of u and v. We used u and v coming from the lemma so that they would satisfy this. So this is congruent to 0 mod p. Okay. Okay. Now, why is it important that we say this is congruent to 0 mod p? So now let's think about what we've said. We are looking at this expression. Okay, it is an expression that lies strictly between 0 and 2 times p, but it is divisible by p, right? But what's a multiple of p that's between 0 and 2 to the p, 2 times p strictly? Well, it's just p. So you have a multiple of p strictly between 0 and 2p, so it has to just be p. Why is that good? Because then p is a sum of 4 squares, as desired, right? So, so we have a multiple of p that is strictly between 0 and 2p, i.e. it must be p, i.e. ux1 plus vx2 plus px3 squared plus vx1 minus u x2 plus p x4 squared plus x1 squared plus x2 squared is equal to p. So p is a sum of 4 squares. As desired. Okay. Okay. So we've shown that any prime is a sum of 4 squares. Now I want to show that any positive integer is a sum of 4 squares using that fact. Now I want to use the fact that any prime is a sum of 4 squares to show that any positive integer is a sum of 4 squares. Okay. So how do I do this? Okay. To do this, I need the following formula. Now this following formula, the following formula is something that you could have actually deduced in like Algebra 1 if you felt like it. There's easier ways to see this formula. So if you know anything about the quaternions, this formula follows from some properties of the quaternions, but you don't need that, and this was known well before the quaternions were discovered. So the formula in question is the following. So if you multiply two sums of 4 squares, okay, what you get is also a sum of 4 squares. So this is AE minus BF minus CG minus DH squared plus AF plus BE plus CH minus DG squared plus AG plus CE plus DF minus BH squared plus AH plus DE plus BG minus CF squared. Okay. So what this formula says is that products of sums of squares are sums of squares. Now, again, where does this formula come from? You could just brute force compute this, but the easiest way to see where this comes from is from the quaternions. So maybe I'll say that quaternions here. Okay, if you're interested, you can see how they come from like that. Apparently, though, this formula was figured out way before that, just through brute force, basically. Okay, so this formula says that a product of sums of 4 squares is itself a sum of 4 squares. Thus, since we know the result for primes, we know the result for any positive integer. Okay. So that does it. Okay. So every positive integer is a sum of 4 squares. Okay. So, before I move on to the next thing that I wanted to talk about, Someone had asked me a question about one of the homework problems I had assigned. So I thought it would be a good idea actually to have a look at it, because it's a pretty good problem that kind of illustrates a lot of the thinking that goes on behind some of this stuff. So this is from chapter 13. This is problem 26. Yeah. So this is a problem on your last homework. So on homework number 5. So this is chapter 13, exercise 26. So it had 2 parts. Here, I'll just show them to you. So let me focus the camera. Okay, so 26 here. So the A part is let P be a prime that's congruent to 2 mod 3. Show that minus 3 on P is equal to minus 1. So that's a Legendre symbol, obviously. So this is saying that show that minus 3 is not a square mod P, right? It's not a quadratic residue mod P. And so the hint there is to consider cases P congruent to 1 mod 4 and P congruent to 3 mod 4 separately. So those are, that is, showing that is relatively straightforward. Basically, it's just computing Legendre symbol. Quadratic reciprocity is going to help you there. So considering these 2 cases separately, or maybe explaining why you can break this down into only these 2 cases is going to be enough. So that's going to pop directly out of there. So then the second part says prove that there are infinitely many primes P congruent to 1 mod 3, and it gives you this hint of letting n be this particular form of number. So a list of primes P, I'm assuming, squared plus 3. Okay, so how do you actually do this, and what does that have to do with the first part? Okay, so I want to prove that there are infinitely many primes P that are congruent to 2, or sorry, not 2. That's true as well, but that's actually easier to show than this one. Infinitely many primes congruent to 1 mod 3. Okay. Alright, so that's what I'm trying to show in the B part. So by the A part, assume that if P is congruent to 2 mod 3, then minus 3 is not a square mod P, i.e. the Legendre symbol minus 3 on P is minus 1. Okay, so suppose that we know this. I want to prove there's infinitely many primes that are congruent to 1 mod 3. So how do I do that? Well, the hint says to define that in a particular form. Of course, when it comes to showing that there's infinitely many primes of some form, the idea that it's referring to is this idea when we first proved that there are infinitely many primes. The idea is suppose not, i.e. suppose that I have a list, p sub 1, p sub 2, all the way up to p sub n is the exhaustive list of all primes that are congruent to 1 mod 3. Okay. Alright, so suppose that I've completely enumerated the entire list of all primes that are congruent to 1 mod 3. Alright, so then I define this big N to be the product of all those primes squared plus 3. I notice? All right, so note, if I define n in such a way, n is congruent to 1 mod 3. Okay, why? Well, 3 is 0 mod 3, and so n is congruent to just this list of products of primes squared mod 3. But each of these things is congruent to 1 mod 3. So this is congruent to 1 times 1 times 1 and so on, squared mod 3. So it's just 1 mod 3. So this n is congruent to 1 mod 3. Now, because I said that I have listed every single one of these primes that are congruent to 1 mod 3, if n is prime, I have found a contradiction here, right? So if n is prime, I have a contradiction. Okay. All right. So, assume n is not prime. Now, what is my contradiction? Well, I said that I've listed all the primes that are congruent to 1 mod 3. But since n is also congruent to 1 mod 3, if n is also prime, and it's none of those primes, okay, because of how it's defined, then I have a new prime that is congruent to 1 mod 3. So that contradicts that list being the exhaustive list of all the primes congruent to 1 mod 3. Okay. All right. So assume that n is not prime. Okay, well, if it's not prime, then it has some prime divisor not equal to itself. So there's some prime p that divides n. But what does that prime look like? Well, note 3 doesn't divide n. Why do I know that? 3 doesn't divide n because n is congruent to 1 mod 3. If 3 divided n would be congruent to 0 mod 3. Right? So since n is congruent to 1 mod 3, 3 does not divide n. Why do I need to list this? Okay, so this is a fact. Why do I need to list this? Well, 3 is the only prime that is congruent to 0 mod 3. So any other prime that might divide n would have to be either congruent to 1 or 2 mod 3, because if it was congruent to 0, it wouldn't be a prime. Right? So there's only one prime congruent to 0 mod 3, and that is 3. Okay, but I've taken care of that. So 3 doesn't divide n. Okay, so any other prime dividing n must be either congruent to 1 or 2 mod 3. Right? So 2. Any other prime divisor of n must be congruent to 1 mod 3 or congruent to 2 mod 3. Those are the only other options once I get rid of 3. Okay. So then we consider each of these two cases. Right? So first case here, no prime p congruent to 1 mod 3 divides n. How do I know that? Because of the way that n is constructed, right? I've said that p sub 1 through p sub n is the exhaustive list of all primes congruent to 1 mod 3, and none of those divide n, right? So no prime congruent to 1 mod 3 divides n, since p sub 1 to p sub n is the exhaustive list of primes congruent to 1 mod 3, and no p sub I divides n by construction. So by the definition of n, no such p sub I can divide n. Okay. Okay. So 3 can't divide n, which is the only number that's congruent to 0 mod 3 that would be allowed. Or only prime that's congruent to 0 mod 3 that would be allowed to be considered as prime divisor of n. No prime congruent to 1 mod 3 can divide n for this reason, because of how n is defined. And so the only other option is that a prime divisor of n is congruent to 2 mod 3. So secondly, the only remaining option is that any prime divisor of n must be congruent to 2 mod 3. Okay. So let's consider this fully on the next page. So let P be such a prime divisor of n. Okay. But then P dividing big N implies that P times K is equal to, well, that definition of big N, which is the list of primes p sub 1 to p sub n multiplied together, squared, plus 3. Okay. What does this mean? So p times k, that's for some integer k. Okay. So, what does this mean? This means that this product, p sub 1 through p sub n squared plus 3, is congruent to what mod p, where p is this prime divisor of n that is congruent to 2 mod 3. Well, it has to be congruent to 0, because I've said that this thing is p times something. It's a multiple of p. So p divides this quantity, and so this product of these p sub i's squared plus 3 has to be congruent to 0 mod p, where p is this prime divisor of n that's congruent to 2 mod 3. Okay, but then that means that this product squared is congruent to minus 3 mod p. So minus 3 is a square mod p. Oh, that's a problem. Why is that a problem? Because by the A part of exercise 26, this Legendre symbol minus 3 on p is minus 1, which explicitly says that minus 3 is not a square mod p. But we've just said minus 3 is a square mod p, i.e., its Legendre symbol minus 3 on p is equal to 1. But this contradicts part A, which says that if p is congruent to 2 mod 3, then minus 3 on p is equal to minus 1. So we have a contradiction. So tracing back through our logic carefully, oh, so yeah, I was asked how do you deal with case p equals 2. So this expression is not even. 2 doesn't divide. You can take care of it in the same way that you take care of you can take care of it separately, just like you took care of the 3 case. Okay. So yeah, it's true that that P is congruent to 2 mod 3, but the Legendre symbol is actually 1 in that case. So this is true for odd primes P, is what we're showing here. But this n is not even, so you can take care of, you basically can take care of that just by definition of n. 2 doesn't divide it. So if you like in your proof, you can include that, here at this step. Right. Okay. So anyway, so tracing back through what it is we said here, we have this n defined in this way. It's congruent to 1 mod 3, but it actually has to be prime because 3 doesn't divide it, as it was noted in the chat. 2 also doesn't divide it. And then, so any other prime divisor would have to be congruent to either 1 or 2 mod 3, and that would be an odd prime divisor since we've already taken care of the 2 case. So, so no prime that's congruent to 1 mod 3 divides it because of how it's defined, because that is the full list, supposedly, of primes that are congruent to 1 mod 3. So none of those can divide n. And the reason that no prime that's congruent to 2 mod 3 can divide n is because then it would say that minus 3 is a square mod p, and it's not. So this is not a square mod p from the first part, from part A. And so what is the thing that went wrong there? The thing that went wrong is, so, what this is saying is that big N is prime, but this contradicts that p sub 1 to p sub n is the exhaustive list of primes congruent to 1 mod 3, since n is also a prime congruent to 1 mod 3 that is not on the list. So there's infinitely many primes congruent to 1 mod 3. So it might seem a little strange that, I mean, because think about what this statement is saying. It's saying that there's infinitely many primes such that when you divide them by 3, you have remainder 1. Well, since there's only 1 prime congruent to 0 mod 3, the only options are being congruent to 1 or 2 mod 3. And we know there's infinitely many primes. So you would think that, showing that there's infinitely many primes congruent to either 1 or 2 mod 3 wouldn't be that much of an issue. And in fact, showing that there's infinitely many primes congruent to 2 mod 3 is something you can think about how you might do. It is easier than this one. But, I sat and thought about a way that might try to be, a little easier to do than this. And I couldn't really come up with one. So it seems like this is kind of the most straightforward way of doing it, even if it kind of seems like a roundabout way. So it's a little funny that, in order to prove this statement about there being infinitely many primes such that when you divide them by 3, you have remainder 1, would basically require quadratic reciprocity, right? You would have to compute some of these Legendre symbols. So this is pretty interesting. Okay. Anyway, so that was an example of one of the homework problems that I thought was good. So next, let's look at kind of the last thing I want to talk about in chapter 15. I wasn't originally going to cover this, but I thought it was interesting enough, and it was a good enough direct example of some of the things that I was going to talk about tomorrow and Friday. So this is Pell's equation. Okay. right. So what does Pell's equation look like? Let D be a positive integer that's not a square. Okay. We wish to find integer solutions. X and y to the equation x squared minus dy squared is equal to 1. Okay. So this is Pell's equation. Now, as I'm going to go over tomorrow and Friday, when we encounter an equation that we are interested in solving in integers, or in loosening our requirements somewhat in rationals, we have some natural questions that we ask. Okay, so one is, does the equation in question have any integer solutions? So that question is answered pretty easily here. So D is a positive integer, D is not a square. Of course, if y is equal to 0 and x is plus or minus 1, we have an easy solution. Okay. These are called the trivial solutions. So really, we're interested in non-trivial solutions. Okay. So non-trivial solutions being integer solutions that are not one of these. So y is not 0, x is not plus minus 1, right? So that's the solutions that we're looking for here. Okay. Okay. So as I said, when we encounter some equation that might look something like this, and we want to ask for solutions to it, we have a list of questions that we ask. And like I said, I'll go over this again tomorrow and Friday. But the list of questions goes something like this. First question is, does it have any integer solutions? So we answered that here. This one has some trivial solutions. But we're actually interested in the more interesting question of, does it have any non-trivial solutions? But in general, it's always nice to ask, does it have any solutions, right? So most famous example, right, if you're looking at the equations that define Fermat's last theorem, it doesn't have any integer solutions. So, that are not, all 0, right? So it doesn't have any positive integer solutions, I should say. So the question of does it have any integer solutions fitting, the constraints that you're looking for? It's the first question. If either you don't know how to show that, or you're a little worried that it might not be the case, another question you could ask is, well, does it have any rational solutions? Right. So does it have any rational solutions? So this is a flimsier requirement. It's more floppy than the requirement that the solutions be integers, because we're allowing rational numbers as well. And then, of course, the follow-up questions are, if it has an integer solution, how many does it have? Does it have like finitely many? Does it have infinitely many? And then the same thing goes for a rational solution. So does some given equation have infinitely many solutions if it has rational solutions if it has one or a couple? All right. So, but looking for these non-trivial integer solutions can be tricky. Okay. Okay. So let's look at a couple of examples. So what about if D is 63? Okay. So if D is 63, we have the equation x squared minus 63 y squared is 1. Okay. So note 8 squared minus 63 times 1 squared is equal to 1. So 8, 1 is a solution. Okay, that wasn't too bad. Right, we could have just done that by inspection, just kind of looking at it. We could have probably figured that one out. What about when D is 61? Okay, so when D is 61, we have the equation x squared minus 61y squared is equal to 1. Surely this is easier, right? D is smaller, right? But the smallest solution is the following. This is 1,766,319,049 squared minus 61 times 226,153,980 squared. Okay, so this solution was found by the Indian mathematician Bhaskara in the 1100s. Okay, you might say, how did this guy in the 1100s compute that this was indeed a solution to this equation? So he discovered a method for doing this that's actually at the end of this section. I don't know that I'm going to go through it in detail, but I may try to. If I don't go through it in detail, then I will leave it to you. You can have a look at how it's done. So maybe I will do that rather than the proof of this fact. So maybe that's more interesting. In fact, this question that I asked does an equation that depends on some parameter d, right? So you get a different equation for each choice of d. The question is, if I choose a d that is not a square, do I always get integer solutions that are non-trivial? And Lagrange was the first to prove this, I think. And it's the following. So this is a theorem due to Lagrange. So let d be a positive integer, not a square. Then the equation x squared minus d y squared equals 1 has a solution in integers xy with x not equal to plus or minus 1. If you toss out x not equal to plus or minus 1, this gets rid of the possibility for trivial solutions. Okay. Okay. So maybe I'll sketch the proof. Okay. So let A be a positive real number. And let B sub A be the parallelogram in the plane given by x minus y times the square root of d. Absolute value of that is strictly less than A. And the absolute value of x plus y times square root of d is less than 3 square root of d over A. Okay. So I can compute the volume, that is the area of this thing, of this parallelogram. So to see what the area of this parallelogram is, I'm going to go back in the chapter. So let me bring this closer up. Okay, so number 2 says, more generally, that parallelogram described as absolute value of ax of 1 plus bx of 2 less than r1 and cx of 1 plus dx of 2 less than r2 has area for r1, r2 over the absolute value of the determinant of that 2 by 2 matrix, A, B, C, D. Okay, so matching that up with our description here, where we have 1 minus square root of d, 1 plus square root of d. So how do we match that up with that equation that we just found? Thus, volume of B sub A, which is the area, is 6, which is greater than 2 squared. We're in the plane. Okay. Right. Since this B sub A is also convex and centrally symmetric, we use Minkowski's theorem. To get the existence of an integer point we'll call x sub A, y sub A, which is not the origin in our set B sub A. Note that such a point satisfies the following: the absolute value of x sub A squared minus d times y sub A squared can be written as the product of these two things, these two quantities in question. Right. which is strictly less than a times 3 times square root of d over a, which is 3 times square root of d, okay, which is independent of a. Okay. We start with a sub 1 equal to 1, okay, which gives us integer points. So get integer point x sub a1, y sub a1, which we define to be x sub 1, y sub 1. Okay, in that way. This leads to a sequence of, so this yields a sequence of points which must eventually repeat infinitely. Okay. Okay. This gives us infinite solutions to the equation x squared plus d y squared is equal to big N. Okay, so we use this to find the solutions we're looking for. Okay, so of course this was all fine up until this last couple of sentences. So if you want to see the details here, this is page 371 and 372. Okay, but this is how it goes. Okay, and the main point, everything else is just kind of some annoying algebra, but the main point is using Minkowski's theorem to guarantee these integer points that are non-trivial. Okay, so a corollary of this theorem is that there's actually infinitely many such non-trivial solutions. So corollary, let d be a positive integer, not a square, then x squared minus d y squared equals 1 has infinitely many solutions in integers. So the proof of exactly how this follows from the theorem is on page 373. But this answers in the affirmative a couple of those questions that I said, one might always want to ask about this. So, how do I actually go about finding solutions? So how do I find solutions to Pell's equation? Alright, if it was done by someone in the 1100s, maybe, your confidence is telling you, like, you could definitely do it in that case, which is true. Okay, you just have to be a little creative. And so, what is the idea? So this is called the Chakravala method. So this is Bhaskara's Chakravala method. Okay, so this says we have, say we have two solutions to these equations related to Pell's equations. So I have solution x1 y1 to the equation x1 squared minus d y1 squared is k1, and another set of solutions to another equation x2 squared minus d y2 squared is equal to k2. All right. So we represent these by triples. And here would be another triple. So these triples for us say that x1, y1 solve this Pell's equation where 1 has been replaced, the right-hand side 1 has been replaced by this k sub 1. The same thing is true here. So these triples can be multiplied. So these triples can be multiplied in the following way. We get a triple x sub 3, y sub 3, k sub 3, where k sub 3 is k sub 1 times k sub 2, and x sub 3 squared minus d y sub 3 squared is k1, k2, which is k3. Okay. And in order to do this, these x sub 3s and y sub 3s, the way that they arise out of the x sub 1s and x1, x2, and y1, y2s are the following. So x sub 3 is x sub 1, x sub 2 plus d y sub 1, y sub 2, and y sub 3 is x sub 1, y sub 2 plus x sub 2, y sub 1. Okay, and you can quickly verify that these equations, these identities work out. Okay. All right. In fact, I mean, to see this, note that x1 plus y1 times square root of d times x2 plus y2 square root of d is equal to x sub 3 plus y sub 3 square root of d. Okay. Okay. So then what is this Chakravala method? So the Chakravala method starts with an arbitrary triple that we'll call A, B, K. Okay, with A squared minus D, B squared equal to K. And that's how we're defining the triple. And the goal is to find a triple with K equal to 1. So if we can do that, then we've solved Pell's equation, right? Because then on the right-hand side, we have a 1 here, and we found integer solutions to Pell's equation. Okay. So, how do I do this? So let E be the GCD of B and K. Right. Suppose this GCD is not 1. Right. If P is prime and P divides E, then since it divides the GCD, it divides B and K. All right, so P divides K plus dB squared, but K plus dB squared is A squared, which means that P divides A and P divides B, so P squared divides A squared minus dB squared, i.e. P squared divides A squared minus dB squared, which is K. So we can divide A and B by P and K by P squared and obtain a smaller K. Okay. We can do this until the GCD of B and K is 1. Okay. Then, now, multiply the triple ABK in the way we talked about multiplying the triples before. Multiply the triple ABK by the triple M1 and M squared minus D, where M is some integer to be chosen. Okay, so this gives the triple AM plus BD, A plus BM, and K times M squared minus D. Okay, so which, after dividing by K, gives the fact that AM plus BD over the absolute value of K squared minus D times A plus BM over absolute value of K squared is equal to M squared minus D over K. Sorry, we're not dividing by K, we're dividing by K squared here. Okay. All right. So you might be asking, like, why are you using absolute value of K here? It's to keep the X and the Y here positive. So keeping them positive integer solutions. But on the right-hand side, you have to have K, because, of course, this is, if we're ultimately going to want the thing showing up on the right-hand side to be 1, we want it to be, we care about the sign here. Okay, ultimately, it doesn't matter how we how we write this. We would be happy with negative integer solutions, but so this is just a technical point. Okay. So then choose m to be a positive integer such that a plus bm is congruent to 0 mod k, and such that the absolute value of m squared minus d is as small as possible. Okay, so I have a lemma. So I'm not going to prove this, but this says that if a plus b m is congruent to 0 mod k, then am, or I should say, am plus bd over k and m squared minus d over k are integers. Okay. The proof of this lemma is on page 374. But what does this lemma say? So this lemma says that our new triple is an actual integer triple, right? So that our new triple is indeed an integer triple. Okay. And thus we can repeat this process until we get a triple with k equal to 1. Okay. All right. So this is the Chakravala method. Now, I've run out of time today, so I will start by doing an example of this tomorrow. The Wikipedia article on the Chakravala method actually has a couple of examples as well, which is nice to see how this works. Because for some of these things, you have to repeat it many, many times. And, as I said, it could be a little bit shocking that some of these equations, the smallest integer solutions are so huge. So asking for positive integer solutions for equations like this can be really tricky. So my hope is, unfortunately, in the time left, I'm not going to have enough time to give you a like really solid basis on elliptic curves. But this is the type of stuff we're touching on. So I'm going to use the first couple of intro chapters from a textbook that I'll reference tomorrow to kind of give you a taste of what it is that this is talking about, and specifically how this relates to some troll math problem that you might have seen floating around the internet that has been cooked up by someone who knows something about elliptic curves and presented in a benign way that's actually it's actually a really hard problem. So anyway, I'll bring that up tomorrow when I'm talking about this stuff. But since I'm out of time, I will stop here. As I said in the announcement, I'll post your final exam tomorrow, and it'll be due by midnight Friday. Although same rules apply, it's a little bit flexible here. But the deadline for me to submit grades is by midnight Monday. So I'm gonna say there's a hard deadline of Sunday afternoon so that I can actually finish submitting all your grades on time. So anyway, that's that, and I will see you all tomorrow.